Hello everyone and welcome to this video in the hands-on large language models series. Today we are going to look at how to use large language models to perform the task of text clustering and topic modeling. To give you an overview of what all we are planning to cover in this series, we are following this book which is titled Hands-on Large Language Models by J. Alamar. And my purpose of making this playlist is so that you understand the hands-on applications of language models. In the previous 3 to 4 lectures, we looked at text classification. So the data set which we had was of movie reviews, and the task at hand was to look at every review and to classify whether the movie review is positive or whether it is negative. We used several types of language models for this. We used representative language models as well as generative language models. In generative language models, we used open source models based on T5, FLAN T5, and we also used closed source modeling approach, which involved making an API call to ChatGPT. Today, our main focus is going to be to start this section number 5, which is text clustering and topic modeling. Similar to the previous section on text classification, I estimate that this section will also take about 2 to 3 lectures. In today's lecture, we are going to start with text clustering, and in subsequent lectures, we will look at topic modeling. So let's get started with today's lecture. First, let me give you an overview of text clustering, what it is, and why it's needed. So the main goal of text clustering is to look at huge amounts of textual data. Let's say you have collected data from Wikipedia articles, Reddit articles, LinkedIn posts, books, etc. And you have this huge data set, right? And you don't know what are the different categories in the data set. You don't know whether the data set talks a lot about animals, whether it talks a lot about sports, whether there is a lot of information about food, etc. Your goal is to look at the data set and to organize the data set into different clusters. So for example, I have shown in the figure here that we took a look at this data set and we divided this data into 3 clusters. The purple cluster which you see over here is the cluster of all the documents which talk about animals like cats or dogs. The blue cluster over here is the cluster of all the documents which talk about sports like soccer, basketball, or cricket. The green cluster here is a cluster of all the documents which talk about food like pasta, pizza, etc. So now this is an unsupervised learning task. When you are given the data set, when you are given the documents, no one tells you that, hey, there are 5 clusters which this data will be clustered into. You have to find out the number of clusters also on your own. And that's what makes unsupervised learning tasks such as text clustering a bit more challenging, I would say, than supervised learning tasks. So the first step is to form this cluster. So let me write here step 1 is formation of clusters. Until this step we have not assigned any name to the cluster, right? And that's the main goal of step number 2, which is also called topic modeling. In topic modeling, what we do is we look at these clusters and we give names or topics to each cluster. So for example, I'm going to look at this purple cluster over here and I have to figure out that the topic name for this is pets. I have to look at the blue cluster and I have to figure out that the topic name for this is sports. I have to look at the green cluster and I have to figure out that the topic name for this is food, right? So the step number 2 is topic modeling. Only when I perform both these steps, it will be useful to me. Now, can you think of any actual application where text clustering will be relevant? Let's say you are a researcher who is doing research on language models and you want to look at all the research papers out there. So you collect all the data set and then you only want to look at those research papers which talk about, let's say, generative language models. We can do that with the help of clustering. How? You take all those documents, you segment them into clusters, and then you find that topic which is related to language modeling or generative language modeling. That's one real life practical application of where text clustering is needed. In fact, if you see all the companies around you like Netflix, Google, Oracle, Meta, Amazon, there are a number of occasions when these companies have to do text clustering. So, for example, if you come across an ad uh, of a document or a website and it's named that keywords, this website talks about these topics. It might be that those topics have come from the topic modeling task. That's why text clustering is needed, and that's why this topic is so important. In this lecture, we are going to see how language models can be used to perform clustering. So, we will explore how to perform clustering with embedding models, and then in subsequent lectures, we are going to look at a text clustering inspired method of topic modeling, namely BERT topic. So, out of the two steps which I showed you, formation of clusters and topic modeling, today our main task is going to just look at formation of clusters. In the next lecture, we are going to look at topic modeling, and there we'll also explore this really cool method which is called BERT topic. So, what do I mean by embedding models? In this lecture, what we are going to do is that we are going to take documents or text data and we are going to convert each document into a vector, and it's also called as a vector embedding. And the model which is used to do this conversion, that's called as an embedding model. So that's called as an embedding model. And then based on these vector embeddings, then we are going to do the clustering after that. And for clustering, we are going to look at different type of methods such as k-means, DB-scan, etc. I'll come to all of these types of methods when we reach this stage. So this is the main goal of today's lecture. So let's get started with the first step. And as always, with all machine learning frameworks and machine learning models, the first step always is to collect the data set. So what's the data set which we are going to use in today's lecture? Well, we are going to look at all the articles which have been published to this website, which is called ArXiV. If you are not familiar with ArXiV, you can go to archive.org. It's that place where you can upload preprints of your research paper. So let's say if you have worked on some research paper and you're really proud of your work, but you don't want to wait till it goes through the peer review process. What you can do is that you can take your research paper and upload it on ArXiV so that it's immediately available to the wider public. So archive consists of a huge number of research papers in different topics. We are going to look at a specific topic which is computation and language. So we are going to look at all the papers which are published within this main section or within this main topic. And it's labeled as cs.cl. So CL is computation and language. Within this topic also, what we are going to do is that we are going to look at 44,949 abstracts which have been published within the cs.cl section from 1991 to 2024. So we are going to look at a 33-year time span, and we are going to look at more than 44,000 papers published on this topic, and we are only going to look at the abstracts of these. So let's say we collect these 44,000 abstracts, and then our goal is to organize these abstracts into different clusters based on what these abstracts are talking about. Already you can see how useful it is, right? As a researcher, if you want to do research in a specific topic within computation and language, this clustering tool or this clustering model which we are going to develop today can help you understand within which papers your particular topic is talked about more, since you will look at only that particular cluster or those clusters. Now, how will we get this data set? One approach, of course, is to take all of these 44,000 papers, copy their abstracts, and download it on your local machine. That will take a huge amount of time. But there is a second approach. Of course, our friend Hugging Face comes to our help. Hugging Face is that place where you will have access to machine learning models, data sets, and it's just the best open source platform and community out there. So there is a particular data set which is called archive underscore NLP, and this is the data set which we are going to use. It consists of abstracts from this cs.cl category, and as I mentioned on the whiteboard over here, it consists of 44,900 abstracts. As you can see here, it also consists of titles. So the data set consists of titles of the paper and abstract. So if you scroll through the data set, you will see the year in which the paper was published, you will see the title of the paper, and you will also see the abstract of the particular paper. So here I'm looking at this paper titled Framework and Resources for Natural Language Parser Evaluation, and here you can see the abstract for that particular paper. Similarly, I can click on any other abstract link and I'll see the title and the abstract. We are just going to directly use this data set from Hugging Face, and that saves us a lot of time and that saves us a lot of effort. You'll see that when you download this data set, it will take up 53 megabyte of space, and you can also read more about this data set, the paper the paper in which this data set was published. This data set is also present on Kaggle. You can read a lot about this data set, but it's just a very popular data set and it's very reliable. So we are going to use this data set right now. I'll take you through the code shortly, but before that, I just want to explain the entire workflow to you so that you can visualize what we are doing. So this is the first thing which we do. We are going to download this data set. That's the first step. The next step is that we are going to implement the text clustering pipeline. The reason I call it a pipeline is that text clustering usually takes place in three steps. So if you visualize this pipe right here, we go from 0 to step number 1, then we go to step number 2, and then we go to step number 3. And this is the text clustering pipeline. What are the different steps in this pipeline? Step number 1 is that we are going to take each of the input document. So when I say input document, you can think of one abstract over here. We are going to take each of these abstracts which I'm showing you on the screen right now, and we are going to convert them into vector embeddings using an already existing embedding model. That's stage number 1. What is a vector embedding? Well, we are going to take documents and we are going to convert them into a flat one dimensional vector, each document. It can be a 300 dimension vector, 700 dimension vector, it depends on us. The second thing what we are going to do is that we are going to take these embedding vectors from a higher dimension and we are going to project them into a lower dimensional space. So we are going to reduce the dimensionality of the embeddings, and for that we are going to use a dimensionality reduction model. The reason this is necessary is that if we just use a very high dimensional embedding, it becomes very difficult to form clusters. And that's why stage 2 is usually implemented, where we take the higher dimensional embeddings and we convert them into a lower dimension. And then stage 3 is the final step of the process, where we are going to find groups of semantically similar documents. So we are going to look at these lower dimensional embeddings and then we are going to find groups or find clusters within them. And then we are going to try to analyze these clusters and try to see what they mean or what they represent. So let's go through each of these stages sequentially and see what exactly is done in each and every stage. Stage number 1 is embedding the documents. So here is a schematic which shows what we are going to do. As I mentioned, we are going to take the documents and for each document we are going to convert it into a vector. So if you look at the first row, that's the vector for the first document. If you look at the second row, that's the vector for the second document. If you look at the last row, that's the vector for the last document. So in step 1, we convert the documents to embeddings using an embedding model. This will be very useful for finding groups of semantically similar documents. Remember that the embedding which we are going to use is a pre-trained embedding which already captures the semantic meaning of words. So it won't be a random embedding. So if two documents are very similar in meaning, their vectors will lie close to each other. If two documents are completely different in meaning, their vectors will have a perpendicular or 90-degree angle between each other. So whatever embeddings which we are doing, they make sense. They capture the intuitive meaning of sentences. How do we get these embedding models? Well, for the purposes of today's lecture, we are going to use pre-trained embedding models which already capture semantically similar documents. So our goal is to make sure that if two vectors are aligned, that means that the vectors carry information of similar documents. That's what will be used later for the clustering purposes. Vectors which are semantically similar will typically lie in one cluster. Vectors which are completely different from each other or have 90-degree angle between each other will lie in different clusters. Now choosing the embedding model is also going to be very important here, because there is a trade off between accuracy and speed. Let's say if you use an embedding dimension of 3000 or 4000, that may lead to more accuracy, but it will reduce the speed. So in the code, what we are going to do is that we are going to use an embedding dimension of 384, and the model which we have selected is so that it has a good accuracy and it has a reasonable computational speed. When I share the code with you, you can of course try with more number of dimensions, because that's always a parameter which you can vary. But for the sake of today's lecture, I'm going to go ahead with 304 dimensional embedding vector for each document, right? So that's the first stage. We are going to take documents and convert them into vectors. Then comes the second stage. As I mentioned in stage number two, we have to reduce the dimensionality of the embeddings, right? And so if you see schematically, what I mean by reducing the dimensionality is, let's say if we are in a three-dimensional vector embedding space, after dimensionality reduction, we are taken to a two-dimensional space. Why do we do this? Because if we have a higher dimensional data, it usually becomes difficult to identify meaningful clusters. That's why it's always better to take the data to a slightly lower dimensional space before we cluster the data. Now, when you think of dimensionality reduction, there are two different techniques which can be used. There is a principal component analysis, and there is another technique which is called uniform manifold approximation and projection, which is UMAP. I'm not going to go into the details of both of these methods, but I'm just going to mention that in today's lecture, we are going to use the second method. You can even try principal component analysis. But for those who are unfamiliar with UMAP, UMAP was a technique introduced later than PCA, but it's actually an awesome technique. So let me just show you a very nice visualization of this technique. So here is a visualization using UMAP, where we take the fashion MNIST dataset. The fashion MNIST dataset is a dataset which consists of images of cloth. It's a 784 dimensional dataset, because every image is 28 pixel by 28 pixel. So if you look at one image here, this shirt, it's 28 pixel by 28 pixel. So each data is 784 dimensional. Now what you can do using UMAP is that you can actually, yeah, you can take this data, this 784 dimensional data, and you can project it to a three-dimensional space. So on the left hand side, I'm showing UMAP, and you can see here I'm rotating it, and here you can see that what I'm zooming in right now is a shirt which has been transformed from a 784 dimensional space to a three-dimensional space. The red is a t-shirt, right? And it's transformed from a 784 to a three-dimensional space. Isn't it awesome? The purple is trouser. So if you see the coat, if you see coat is green, and you'll see shirt is red. So green and red are a bit closer to each other. See, green and red. But if you see purple, which is the trouser, if you see over here, this is the purple, it's very far away. This is because trouser is very different than shirt or a coat, right? That's what I mean when I say that vectors embed information. So these vectors in three-dimensional spaces, although they are compressed from 784 dimension, we lose the data, right? But still we retain some amount of information, such as the meaning. So t-shirt and coat will be much closer than, let's say, t-shirt and trouser. These kind of things are very useful. So this is how UMAP does dimensionality reduction. I can even scroll down a bit and show you the 3D zooming. So here you can see that it's automatically this thing on the left. On the right, it's another method called TSNE. But if you focus on the left, you will see that uh, yeah, this thing on the left, that is the UMAP. This is exactly what we are going to do. We are going to take the documents from a higher dimensional space, from a three-dimensional space, and we are going to project it into a lower dimensional space. And for making this transition from a higher dimension to a lower dimension, we are going to use UMAP. I'll maybe make separate videos later on the differences between principal component analysis and UMAP. But the main goal of this lecture series is hands-on LLM. So instead of diving deeper into every single aspect of the theory, my main goal is to make sure that you understand the practical implementations of what we are trying to do here. So that's stage number two. In stage two, we are going to reduce the embedding dimensionality using UMAP. And in stage number three, which is the final stage, here we are going to do the clustering. Now, here again, the goal is to take the documents and to form clusters. And we also need to exclude the documents which do not form part of any cluster, like these gray documents which I'm showing using arrow. Now, for clustering also, there are two types of methods. There is a k-mean clustering which we can use, and there is a density-based methods. The problem with k-means based methods is that we need to know the number of clusters beforehand. That's one problem. And the second problem is that k-means clustering does not deal with outliers such as these. It cannot classify outliers into as that they don't belong to any class. These are the problems with k-means clustering. And we don't know the number of clusters beforehand. As I told you, it's unsupervised learning. That's why density based methods are generally preferable. And we are going to use density based clustering methods here. These methods freely calculate the number of clusters, and we do not have to force data point to be a part of the cluster. So, for example, if some points don't belong to any cluster, they will be classified as outliers. This is different than the k-means based methods, which are centroid based methods. Here, all the points are forced to be part of some cluster, which is something we don't want. Another advantage of density based methods is that, let's say if you have data set like this, if you have a data set like this, here clearly there are two classes, right? This upper hemisphere is one class, the bottom hemisphere is another class. But if you use k-means clustering, it does something like this. It says that the blue is one class and the red is another class. This is completely wrong, because this is a distance based approach, it's not a density based approach, and that's why it makes this error. Whereas if you use a density based approach, you can see that it clearly classifies the blue into one category, which is the upper hemisphere or semicircle, and the red as another category, which is the lower hemisphere or lower semicircle. That's the advantage of density methods used over k-means methods. Now, within density based methods also, there are two types of density methods. There is this method which is called as dbscan, and there is another method which is called as HDBScan. So dbscan stands for, it's a very big full form. It is density based spatial clustering of applications with noise. And HDBScan stands for hierarchical. So you just add hierarchical in front of dbscan. So HDB scan allows for dense microclusters to be found without having to explicitly specify the number of clusters, and we can also detect outliers in the data. So we are going to go with this method HDB scan. There is a difference between HDB scan and DB scan. So for example, DB scan, if you take DB scan, it struggles with different densities, as you can see over here. If there are three clusters with different densities, DB scan struggles with that. But HDB scan is robust to different densities. So here you can see density of this cluster is much higher than this cluster. And if you just use DB scan, it makes all kinds of errors. But if you use HDB scan, it clearly classifies these three clusters as three types. Due to all these reasons, we are going to go with a density based clustering approach, and within that, we are going to use the hierarchical density based spatial clustering of applications with noise, which is the HDB scan method. And then finally, the last step is that after we get the clusters, we are going to inspect every cluster to see what it represents. So just to recap the three stages, the stage one is we are going to embed the documents, take the documents and convert them into a 384 dimensional vector. Then we are going to reduce the embedding dimensionality. We are going to go from the 768 dimensional space, and we are going to go to a 5 dimensional space in the code. For that, we are going to use UMAP, which is Uniform Manifold Approximation and Projection. Once we are in a lower dimensional space, then we can employ clustering. And there we are going to use a density based method. In particular, we are going to use the hierarchical density based spatial clustering of applications with noise, which is the HDB scan method. And here is a nice visualization of how DB scan algorithms actually work. So if I click on go, here you see based on the density of points which are closer to each other, clusters are formed. So instead of just radial distances, here we look at densities. That's why these are called density based approaches. I can look at, let's say, smiley face and click on go. So here you see the points which are closer to each other, they are in one cluster. So you can see all of this outside circle belongs to a red cluster, as is being shown in the animation right now. And then we will see that inside there are three other clusters, right? Detecting this pattern using k means would have been very hard, because it's just a distance based algorithm. But using the DB scan, since it's a density based algorithm, you can see that after the first cluster is detected, then we start looking at the second cluster, which has been shown in the blue color on the screen right now, as you can see. And then we'll look at cluster number 3 and cluster number 4. Isn't it awesome? So this is density based DB scan method. HDB scan is even better than this, but for the sake of visualization, you can assume that HDB scan does something similar as what you see in this video. Okay, now that you are familiar with this workflow of what we are going to implement, let us jump right into code and let us code every single step of this process. So this is the Google Colab notebook for the code which we are going to implement in today's lecture on text clustering. We are following the hands-on large language models book by J. Alamar, and as has been mentioned here at the start itself, we will need a GPU to run the examples in this notebook. So what I'll suggest is you can click on the runtime, click on the change runtime type, and then click on T4 GPU. This will be free. It won't cost you anything, but it will just accelerate the process of running this code by a lot. By default, this option will be set to CPU. So you will want to change that from CPU to the T4 GPU. That's the first thing. The next step which you will have to do is you will have to install the packages. For today's lecture, we will only need the data sets and the data map plot, but I recommend to go ahead and install bird topic datasets, OpenAI and data map plot, because all of these will be needed anyways for the subsequent lectures. So you can go ahead and click on this arrow symbol over here. This will download all the requirements and it will install it on your Google Colab. This process might take around 3 to 4 minutes. The next step, as I mentioned, for any machine learning project, what we have to do is that we have to first download the data set. As I mentioned on the whiteboard, we are going to use the ArXiV articles as data set, and in particular, we are going to use this ArXiV NLP data set from Hugging Face. So there is a very simple way to download Hugging Face datasets into Google Colab. We just take this link over here, and then what we can do is that we can use the load dataset function, which is provided by the datasets package from Hugging Face. We can provide this link over here, and then we can provide train, because the dataset is stored in this dictionary called train. So we have to specify the name here called train, and then we can extract the metadata from this dictionary, dataset dictionary. The keys will be abstracts and titles. So as you can see on this website, every uh, every research paper is associated with a title and an abstract. So you can recover the abstracts for all the research papers and the titles for all the research papers. When you run this different code cells, when you run this code cell, all the abstracts and the titles will be downloaded and will be accessible to you through Google Colab. That's the first step. We download all of these archive articles. So after this step, 44,949 training data samples will be available to you. Both the abstracts and the titles will be available. For this lecture, we are only going to deal with abstracts in the subsequent code, because we want to cluster based on the content which is present in the abstracts. So now let us go to the next step. Before doing that, I want to show you this commented thing. So what I did was, along with the code which we are doing in today's lecture, which is analyzing archive research papers and their abstracts, I also ran the same code for Twitter. So I looked at tweets, and then I found a data set from Hugging Face which can extract the different tweets and their sentiments. So my main goal was, can the text clustering pipeline which we are implementing today, can it be used for tweets, and can it be used for tweet sentiment classification? I'll not go through this code in this lecture, but when I share this notebook with you, this code will also be available to you. So with this same notebook, you can implement two projects: the archive dataset project and the tweets project. Now let's start going through the entire pipeline which is implemented for text clustering, starting with the stage 1, stage 2, and the stage 3. The first step of the pipeline for text clustering is embedding the documents. So what we have to do over here is we have to take the input documents and we have to convert the input documents into a vector. So if we have a 44949 input documents, we have to convert each of these documents into, let's say, a 384 dimensional vector or a 700 dimensional vector, etc. Now, one very important thing as a machine learning engineer, which we have to decide here, is what is the embedding model which we are going to use. If you go to Hugging Face and if you search embedding models, you will get a huge list of embedding models. But it's usually difficult to decide among these embedding models what is the embedding model which I should use. And there is a framework which I follow to choose the embedding model. So you can go to this place which is called mteb slash leaderboard. This is massive text embedding benchmark leaderboard. Here you will see the different embedding models, you will see the ranking of these models, and you will also see the size. So the way I choose the model is a trade off between the model rank and the model size. Usually the best is the model which is ranked high and whose model size is low. So if I am running an embedding model using a T4 GPU, which is free on Google Colab or on my CPU, I typically prioritize for a lower model size so that the model can run seamlessly on my laptop, and a lower memory usage as well. Even memory usage becomes important since your RAM comes into question. So if you are using a normal traditional machine and if you want to use a T4 GPU on Google Colab, which is free, or a CPU, I would suggest to go with models which are less than 50 million model parameters, and let's say which take about 700 megabytes to 1 gigabyte of memory. That's my typical cutoff which I use. So the model which we are going to use today is this model which is called the GTE. This model is the GTE small model, general text embedding model. And if you look at the number of downloads, it has around 700,000 downloads just last month, which indicates that the model is very popular. Second, the model size is 33.4 million parameters, which is less than the 50 million benchmark which I use. And if you look at the model size itself, it's about 0.07 gigabytes, which is around 700 megabytes of space. So this looks doable for a T4 GPU and or even on your CPU. Now when I share the code file with you, you can feel free to experiment with different model names also. There is no reason why we should only stick with GTE small. You can try E5 base version 2, you can try E5 small version 2. But remember, if you go ahead with sentence T5 XXL or SGPT, these are huge models because the model size is 10 gigabytes, 28 gigabytes. Make sure you have that much space and that much computing power available on your laptop to be using these bigger models. But for example, E5 small version 2, E5 base version 2, uh, then all MPNet base version 2. This is a very popular and a good model, so you can use this one also. All of these models are workable and you can go ahead with any of these. So if I jump back to Google Colab right now, to use a particular model, what you have to do is that you have to take this URL. So this is the NLP slash GTE small. You have to copy it and then you have to pass it to the sentence transformer function. So you can import the sentence transformer from the sentence underscore transformers package, and then you pass in the link to the model which you are going to use. So this is the embedding model, and then you have to use the embedding model to encode the abstracts which you have downloaded in the first step. So then what this will do is that it will take every abstract and then it will convert it into a 384 dimensional vector. How do I know it's a 384 dimensional vector? Because all of it is mentioned in the model card. If you see GT is small, see it's 384 dimension. This is the model dimension. If you use E5 base 2, it's a 768 dimensional vector. But here I know that since I'm using GTE small, every document will be converted into a 384 dimensional vector. So since I have 44949 documents, each of them will be converted into a 384 dimensional vector. So the embedding matrix shape will be 44949 rows and 384 columns. So that's what this one line will do. So if you run this code, you will first have to download the embedding model itself, and that takes around 70 megabytes, if I'm not wrong. Yeah, 0.07 gigabytes, which is around 70 megabytes. It's very reasonable. And I'm sitting in a space which is around 90 to 100 megabytes speed, internet speed. So it's very fast here. But the speed may be more or less based on the internet connection in your place. But this last step, which is taking every abstract and converting it into a 384 dimensional vector, that takes time. So please be patient during this step. But once it's done, you will see based on the progress that all green bars are there, which means that this step has been done and every abstract has been converted into an embedding vector. You can print out the shape of the embeddings matrix and you'll see that we have 44949 rows, which are 44949 documents, and every document is associated with a 384 dimensional vector. Great. Now we can move to the next step, which is reducing the dimensionality of the embeddings. In this step, what we'll be doing is that we'll be using the UMAP procedure. And as we saw in the on the whiteboard, UMAP stands for Uniform Manifold Approximation and Projection, where we take the documents which are currently in a 384 dimensional space and we have to put them in a lower dimensional space. So what we are going to do is that we are going to take the documents in 384 dimensional space and we are going to convert every document into a 5 dimensional vector. So the way to do this is that from the UMAP library, you import uppercase UMAP and then you call this function. First, you define a UMAP model, and in that model, you have to specify the number of components. This n components indicates the dimension you want to project it to, the lower dimension. So we are going to project it to a 5 dimensional space. That's why n components is equal to 5. The minimum distance is 0 and metric equal to cosine. I'm not going to go into details of these two parameters, but just note that since the metric is equal to cosine, we are going to use a cosine similarity to do this dimensionality reduction. And random state equal to 42 is just so that the code is reproducible every time someone runs it again and again. Once the UMAP model is constructed, we have to use this function UMAP model dot fit underscore transform, and then we have to pass in the embeddings. What this will do is that it will take every 784 dimensional vector and it will transform it into 5 dimensions. So if you print out the shape of this reduced embeddings, you will see that it's 44949 rows and only 5 columns, because now we have transformed from the 384 dimensional space to a 5 dimensional space, right? So the second step has been done, which is reducing the dimensionality of the embedding. And the third step is cluster the reduced embeddings using the HDBScan, or the hierarchical density based spatial clustering of applications with noise. So here you can see that from HDB scan we import uppercase HDB scan, and then to implement this clustering we have to just pass in the minimum cluster size, which means that if our cluster has less than 50 documents, it won't be classified a cluster. We need a minimum of 50 documents in one cluster. Here you can see we don't even have to pass the number of clusters. That's one advantage of HDB scan. And it will also, if some document does not belong to a cluster, it will classify it as outlier, which is exactly what we need. These functionalities are not provided by k-means clustering. In k-means clustering, we have to specify the number of clusters, and it also does not know what to do with outliers. It forces every point to be part of some cluster, which is what we don't need. So then, apart from the minimum cluster size, you have to do HDB scan dot fit, and then you have to pass the reduced embeddings. What this will do is that it will take the reduced embeddings and then it will organize every document into clusters. And then you can print out the number of clusters, and you can see that here we have 150 clusters. That means that of all the abstracts from the 44,949 abstracts on archive, we have converted those into 150 clusters. In currently all the three steps have been implemented, right? We started with converting it into embeddings, then we reduced the embedding dimension, and then we clustered the embeddings. Now only last step is remaining, which is inspecting the clusters. So up till now we are at a stage where, okay, we have 150 clusters, but what do these clusters mean? Why are they useful to me? Let us start inspecting the clusters to know a bit more about them. In the last part of today's lecture, let us start inspecting the clusters which we have obtained so far. Initially, we'll employ a manual inspection technique. So what I'm going to do is that I'm going to look at the cluster 0 and I'm going to manually inspect the first three documents in the cluster 0. So here you can see that we are looking at cluster number 0 over here, and we are printing out the abstracts of the first three documents in that cluster, and we are restricting each abstract to 300 characters. So here are the 300 characters of the first abstract, here are the 300 characters of the second abstract, and here are the 300 characters of the third abstract. Now, can you look at these three abstracts and can you try to think why they belong to one cluster? What are the commonalities between these three abstracts? Okay, so the first abstract seems to be about sign language. The second abstract also talks about sign language. And the third abstract also talks about sign language translation. So it seems that cluster number 0 is a cluster of sign language and all the abstracts which talk about sign language. Isn't that awesome? Without specifying anything to the unsupervised machine learning model, automatically it has figured out that sign language is a common pattern coming up in all the documents and more than 50 documents, because the minimum cluster size is 50, and I'm going to classify all these into one cluster. So this is cluster 1. If you type, let's say, another cluster, let's say cluster 50, maybe there is another common thing between all those documents in cluster 50. That is how clustering actually works. And here we can see that it is working because there is clearly a common pattern between these three clusters. As I told you, parallelly I'm running this clustering on Twitter, the tweets, right? So here what I've done is that I've taken cluster number 10 and I've printed three tweets from cluster 10. You can see that all three tweets talk about Frank Gifford, which is a famous American football star and broadcaster. So this also is incredible because we did not specify that cluster 10 has to be about Frank Gifford. This is automatically chosen by the clustering algorithm. It looked at all the tweets and it saw that, hey, many tweets seem to be about Frank Gifford. So maybe I'll organize all of these into one cluster. Now, there is an obvious problem with this approach because manually we cannot inspect many clusters, right? We cannot manually look at 150 clusters and say that, okay, first cluster is about sign language, second cluster is about some other topic. That's why in the next lecture, we are going to learn about something which is called as topic modeling. What this will do is that it will look at every cluster and then it will automatically assign a topic to that cluster without manual intervention. That will save us a lot of time and effort. Now imagine if you are a researcher who is doing sign language research, you only need to look at cluster 0 now. You don't have to look at all the other 149 clusters. That saves you a lot of time and effort. This is a practical implementation and advantage of text clustering. We can go one step further and try to visualize our clusters. So currently visualization is a bit problematic because the dimension, we are in a 5 dimensional space. So what we are going to do is that we are going to take the 384 dimensions and first transform them into 2 dimensions so that we can visualize. We are not going to change anything about the clusters. The clusters will remain the same, but we are just going to visualize in a 2 dimensional space. So we will take the reduced embeddings in a 2 dimensional space, and the clusters themselves will break it into two data frames. One data frame with all the points belonging to some cluster and another data frame for all the outliers. In HDBScan, if a label associated with a point is -1, it means that it's an outlier. So all the points which have label associated with -1 will be in the outlier data frame. All the points which label not -1, they will be in the clusters data frame. Once we obtain these data frames, we are just going to plot the outliers with the gray color and the clusters with different colors. So all the different clusters will have different colors. And here I am showing the plot. So you can see all the points belonging to the brown cluster. Then this is the pink cluster. Here's the purple cluster, the yellow cluster, the blue cluster. And you see all these gray dots here. Those are outliers, which means those are the points which don't belong to any cluster. Now, I don't know what each of these clusters represents because we have not yet done topic modeling. In the next class, we'll look at all of these clusters and we'll automatically assign topics. So we'll figure out what this brown cluster represents. What does it mean? Maybe one of these clusters is the sign language cluster 0, what we saw earlier. But right now, I don't know which of these clusters is what topic. But this brings us to the end of today's lecture, where we started with 44,000 or 44,949, I think. Let me see the number of abstracts. Yeah, 44,949 abstracts, and we converted them to 150 clusters. All those clusters have been visualized here right in front of you. And all of this was done in a three-step pipeline. First, we started with stage one, which is embedding the documents. The second stage was reducing the embedding dimensionality. And the third stage was clustering the reduced embeddings. In each stage, you have to make a choice as a machine learning engineer. In stage one, you have to choose which embedding model you have to use. So always make a trade off between rank and the model size. In stage two, you have to choose whether you have to use PCA or UMAP as your embedding dimension reduction technique or a model compression technique. I use UMAP here, but maybe PCA might be good for other problems. You can even try PCA here and compare between these two techniques. And the last step, you have to choose whether you have to use k-means based approach or density based approach. The density based approach work just fine over here because a k-means based approach requires us to know the number of clusters and it cannot also deal with outliers. Density based approach satisfied both of these things, and that's why we went ahead with this. Maybe in some other problem, k-means is better. So it's always good to be aware of the advantages and disadvantages of both approaches instead of blindly using any approach. So thank you so much, everyone. In the next lecture, we'll be looking at topic modeling and we'll look at BERT topic, which is a topic modeling framework. It's going to be a very exciting lecture, and I look forward to seeing you in the next lecture.